Hi guys, my name is Austin Fletcher. I am the group lead for Section 2, Experiment 2. It's the Reynolds pipe experiment. These are my group mates right here. Alright, the purpose of this experiment is to correlate the Reynolds number with three different pipes that we're going to be using today. We're going to be looking at the internal flow to calculate the Reynolds number. This is used a lot in industry for when you size pipes, when you size the pumps for them. That way you know the amount of pressure drop throughout the pipe that you're using and the pump that's needed to get the correct pressure that you need. Doing this in class today, we're going to be using a dye test, which is you drop a needle into the middle of the pipe and it releases a dye throughout, so you can see the laminar versus turbulent flow, which we'll get to in a second. Like I said, there's two different types of flow. The first one that I'm going to talk about would be laminar flow. It's when most of the fluid elements are flowing in the same direction. It's generally at a slower speed. This means that all of the fluid elements are flowing in the exact same direction. There's not going to be much play going up and down or any microcurrents, as you'll see later. There's little energy loss throughout this flow. It's great. We don't have a whole lot of entropy generated throughout this flow, which causes little pressure drop along the pipeline. The other type is turbulent flow. It's similar to laminar flow, but like I was saying, this one actually generates the microchannels. When you generate the microchannels, as we all know, entropy is the order of chaos. As you introduce microchannels into it, the entropy will increase in that, and so you'll end up losing energy as it converts to entropy, and then that will actually end up causing you to, the mixing will dissipate the energy, and then it causes a higher pressure drop as you go through the pipe. So if you have a really long pipe in industry and you're pumping oil or whatever else you need to do, you'll be losing a lot of pressure as you try and go hundreds of feet, even miles. Laminar flow you'll generally see with oil bearings or even in your engines to try and lubricate the pistons. This is the dye test that I was speaking of a little bit ago. The dye is put, you can consider this a dye needle. This is the reservoir up here. The dye needle goes directly into the pipe in the middle. For our experiment, we're going to have to wait. Once we turn on the water, you got to wait a couple minutes for the water to get going, and then you have to turn on the dye and let that settle throughout, because if you start taking the experiment right then, it'll show up pretty much as turbulent flow. You have to let everything settle in and equalize first. But anyways, as you can see right here, this is laminar flow. It's the first one. Everything is in a straight line. There's not much play up and down. This is the transitional period right here. This occurs at approximately 2,000 for the Reynolds number. Depending on what reference you use, I used the in-class materials, which said the transition starts at about 2,000 Reynolds number. Earlier we saw a presentation where it's 2,300. It just depends on the reference that you're using. Both in industry, those are very acceptable numbers to use. The transitional, you can see it starts waving a little bit. Eventually it will start folding back on itself. That's called the Kelvin-Helmholtz. The turbulent flow is when it starts flowing throughout the entire span of the tube. Both at the very top and very bottom, you will see dye. So Reynolds number, it's a dimensional, it's a non-dimensional number. So it's very useful when you're trying to size the pump, like I said earlier, or when you're trying to choose a pipe. Other reasons you would like to use it is for dimensional analysis, for different numbers like the Grashof number, and there's a few others in there that helps correlate all this data that you end up getting. So, a little bit about the experiment. The first one that we're going to be doing is the Reynolds pipe. It's a circular pipe. The next one is a hydraulic diameter. That's a non-circular pipe. I'll go into that a little bit more, but you're going to observe a dye stream about 1.5 feet downstream after you let it settle. The maximum laminar flow rate is what you're going to be looking for the first two, the Reynolds and hydraulic diameter. It's when you have a little bit of small oscillations in the stream. That's the maximum. Now, the vortex swirls, this is the transitional region that we were talking about a second ago. That's going to occur about 2,000, 2,300. And then finally, fully turbulent flow, we're looking for that minimum number right there. So we're hoping to be at about 4,000 Reynolds number, somewhere around that range. It depends on the pipe. All right, then we're going to calculate the Reynolds number for each of those, and hopefully you'll see at the end of this presentation I did a sample calculation, and hopefully we'll have the correct one. And we're going to repeat this 5 times so we have an accurate amount of data points to make sure everything works. All right, this is the equations that we were given for the Reynolds and hydraulic diameter pipes. The Reynolds number is going to be calculated from density, velocity, the diameter, and the viscosity. So for the hydraulic diameter, you can relate that to a circular pipe using the appropriate diameter. So what this equation will end up doing is if you have a non-circular pipe, you can convert that as if it was a circular pipe and get the correct Reynolds number. It will end up being higher, but you can correct it, relate them through this method right here. All right, hydraulic diameter pipe, like I said, can be converted. Now this is the orifice meter. This calculates the pressure difference throughout a pipe. This is what we're going to be using through the experiment. It's a small opening right here. There's a difference in diameter right here, as you can see. The first pressure point is going to be before the orifice. So in your normal pipe, it's just a very small pressure tap, as it says right here. Then there's another one right after the orifice. The difference in pressure shows you the flow rate throughout. So if you take the pressure of one, normally there's going to be a transducer up on top. It doesn't show it right here. It'd be a transducer or a manometer tube, something like that, to measure the difference in pressures. There are different ways of doing this in industry that help cut down on the pressure loss and all the currents that are generated because of this. Generally a Venturi tube or something like that, but for this experiment we have the orifice tube. All right. Now this is the equation that you'd use. Q would be the flow rate and K is the parameter given by the orifice meter. That normally comes from specification charts or something like that they give you. And you can see the change in pressure would be right here. Density of the liquid is at the bottom. All right, these are the given parameters that we were given for this experiment. In the literature that we were given, there's 2 different, it said it was a 3/4 inch pipe, and then right here it also said it's a 0.82 inch diameter pipe. So I used for my calculations in a second the 0.82, just so we know. Just a little bit of a rundown of how this experiment's going to go. We're pretty much, like I described earlier, we're going to turn on the water, let that settle, turn on the dye, and wait a minute or 2 for that to settle as well. And then we're going to go ahead and adjust the flow rates. We're going to calculate the maximum laminar, so when it starts to hit transition region, and then we're going to calculate the minimum turbulent region, so we know where both of those are at. After that, we're going to get to the orifice pipe, and we're going to calculate the pressure difference that happens between the laminar and turbulent flows. And this is my sample calculation. I had to make a few assumptions. I used an old chemical engineering fluid dynamics book for some of the values, which should be okay. All right, so we take this equation, we rearrange it to find the velocity. Now, for the Reynolds number of maximum laminar flow would be 2,000, and for minimum turbulent would be 4,000. I'll show you that in a second right here. Now, this is the viscosity I used right here. I used all English units for this calculation, density, and then the diameter of the pipe. So I entered these in here. I did convert everything to feet and pound mass, but I got the velocity to be 0.316 feet per second, and then I got, for 2,000 Reynolds number, and then I got the velocity to be 0.63 feet per second for the minimum turbulent, which if you convert it over and you use Q equals VA, you're able to get the gallons per minute that would be going into it. And I got 0.07 gallons per minute for the maximum laminar flow, and I got approximately 1 gallon per minute for minimum turbulent flow. We can double check these as the experiment goes on. They do seem fairly low, but as I stated earlier, the laminar flow is much less than what the turbulent flow is needed. And generally we'll be able to use these values from what we're using in industry, whether we're pumping oil, chemicals, anything like that. It's a good idea to know a good understanding of what's happening in the pipe so you can have an idea of what you need to get the job done. Questions? All right.